When we started trig, we were limited to right-angled triangles that had angles between 0 and 90 degrees. And any angle that went over 90 degrees, we then split it up into a smaller angle and ratios. Well, our first step was to look beyond right-angled triangles to different sizes of triangles. And this second step will be to look at angles that are bigger than 90 degrees and even bigger than 180 degrees. And we do that with something called the unit circle. And the whole purpose of a unit circle is to look at what happens when we go farther around the circle than just in the 90-degree area. So I have a little program here where I've drawn a unit circle, and a unit circle is special because it has a radius of 1, and that is simply because it makes all the calculations easier. Because if you think about the radius of 1, then whatever triangle I draw, if I'm going to use this and draw a line from the center out to my point P over here, then I get a nice little right angle triangle over here. And whatever triangle I draw, if I move P around, I can move it over here, I'll get a slightly different triangle. Yeah, it always makes a right angle triangle. Of course there's two of them, but we're just going to look at the bottom one. For whatever triangle I draw, this hypotenuse here of my right angle triangle is always equal to 1. So wherever I go around the unit circle, I take it over here as well. Even here, the hypotenuse is still 1. Yeah, and I've also got a point on the bottom half of the circle, which we can't quite see. Let's see if we can, sneaking out there. Okay, over here too, if I drew a line from the center out to here, the radius is 1, so no matter what happens, the hypotenuse of our little triangle is always 1. Yeah, and the advantage of this is we're always counting the angle from the x-axis up to the line. So if I stay in this quadrant, in this first quarter here, then I always have an angle between 0 and 90. Here, if I bring the point down to the bottom here, then my angle would be 0. And if I bring the point all the way up to the top here, then my angle is 90 degrees. So now I can take the point and go beyond 90 degrees and see what happens. So here as well, the angle would be from 0 all the way to this line. So this is going to be a little bigger than 90. Yeah, and all the way up to 180 over here. And then taking this point further, I can extend it beyond 180 all the way down here to 270. And then moving it all the way over here, and we consider going once around the circle to be back to 0, or you could think of it as 360 degrees. Okay, I'm going to pull this point back into the first quadrant again. And now, thinking of this from the unit circle point of view, we have a few different definitions for sine and cosine. We can think of these things a little bit differently than we have until now. We're still working off of a triangle here. From my point around the unit circle, I draw this little triangle. And now if I look at sine, sine is the opposite over the hypotenuse. Remember, the hypotenuse is 1, so let's look at what happens here if we do that. Unit circle is a circle with radius 1. Let's write that down first. And here's what happens if we have that. We have a triangle like this in the circle that you just saw. The radius is 1. And I have my angle here that's going up from 0, from the x-axis, up to this line. And now if I call that angle theta, then if I take the sine of that angle, take the ratio, the opposite side, we don't know what that is, let's call it y, because it will be equal to my y coordinate on the unit circle. Let's call it y for now. So it's equal to the opposite over the hypotenuse, remember from part of SOHCAHTOA. So the opposite is y and the hypotenuse is 1. Well, dividing by 1 just gives me the number back again. So in this case, the sine of theta is equal to y. Going back to the unit circle, you'll see that this y value here, from the bottom axis up to the top point P, that y value is the opposite side of the triangle. And so I can go over here and actually read the sine value, or the y value, off of the unit circle. And it will be 0.8, that's 0.9, maybe that's 0.82, depending on whatever angle this is. Okay, I can do a similar thing for cosine. Remember on a triangle that cosine is the adjacent, so let's call this the x-axis of our, or the x value, x coordinate of our point. Here's our point P. And cosine is going to be the adjacent over the hypotenuse, so that's going to be x over 1. And so again, we get a simpler version of cosine. Cosine of theta is equal to x. So we actually have coordinates for our point P that are made up of trig functions. The x coordinate is cosine theta, and the y coordinate is sine theta. We're missing a ratio, aren't we? We haven't talked about tangent yet. Tangent is a little bit of an interesting one, a little bit different. We won't use it too much at the beginning, but at least just to complete the circle and talk about tangent a little bit here too. We'll look at where tangent comes from. And the name tangent actually comes because it has something to do with the tangent of this unit circle. Take a look at this line over here. It's a tangent to the circle at the x-axis. It's just touching it at one point. That's the definition of a tangent, that it just touches the circle at one point. And if I extend this line that goes from the origin to my point P, and I've got too many things highlighted, let's just get origin to point P, and we're going to construct a line from there. Then the tangent is the length here on the y-axis of where this tangent line intersects with this point P. Since it's off our graph at this point, I'll bring point P a little farther down. So that point here, the length of this to this, and we could measure that from here to here. So this value I get over here of 0.87, that will be the tangent of the angle that this line is at from 0 up to here. So if I move it, then you can also see my tangent changes. So my tangent gets bigger and bigger as I go up to here, and in fact, up there it gets very, very large, and then goes back down to 0 again when it reaches 180 degrees. Okay, so there's tangent. Tangent is the length, the y coordinate when you extend the line to intersect with the tangent. I can then use the unit circle to answer a number of questions. Like for example, if I wanted to find out a trig ratio of an angle that's bigger than 90 degrees, if I want to know the ratio, for example, of sine of 180 degrees, or cosine of 270 degrees, then I can go to my unit circle and see what's happening. So sine of 180, if I go over here, remember sine is the y coordinate. So what's my y-coordinate going to be here over at 180 degrees? Well, it's not high at all. It's way over here, but it's not up or down at all, so that's actually 0. So going back to my problem here, the sine of 180 is equal to 0. If I do the same thing for cosine, but now we want the cosine of 180, then cosine over here is the x-coordinate, and that's minus 1. So I could have also done cosine of 180, and that would have been equal to minus 1. So if I do cosine of 270, here I have to go way down. I'll have to take my lower coordinate point and bring it all the way down here. Down there at the bottom, the x-axis is not left or right, it should be right on the middle of the line, and so cosine of 270 is actually equal to 0. Sine, on the other hand, of 270 is equal to minus 1, because now the sine value is way down at the bottom.